also a postdoc. I'm the astronomy department at UT Austin. And today I'm going to talk to you about something a lot of astronomers are really trying to understand and uncover, which is the black hole origin story. To begin with, just to put us on the same page, what is a black hole? I'm sure you've all heard of black holes, know what it is, but just to define it, it is a region in space where gravity is so strong that not even light can escape. So gravity is what is holding us all here on Earth. That's why you're not flying away. And it is very dependent on how much massive an object is, how much mass it has, how much matter it has, and how densely packed it is. So more matter you have, the more gravity you have, and so you can have an object that has so much mass, so much gravity, that even light, the fastest thing in the universe, cannot escape. So that is what is a black hole. You've seen pictures of black holes. This is the famous one from Interstellar, and this is an actual image of a black hole. And so black holes are very much real. They aren't a figment of our imagination. We've taken pictures of them. We know them pretty well, and we can understand them pretty well. There are two kinds of black holes. The first one is what are known as stellar mass black holes. So these are pretty well understood. They are formed when massive stars die, and then we have plenty of them in our own galaxy, the Milky Way itself. So there's a lot of them. They are smaller, so they're about 160 times more, about 100 times more massive than our sun. But the hero of today's story is another kind of black hole, which are supermassive black holes. So as the name suggests, it's supermassive, and they are found at the center of every massive galaxy in our universe, including our own Milky Way. So they're very extreme, very energetic, not like stellar black holes. They have a lot of energetic activity. There's winds and jets and other things that can be powered by them, a lot of gravity. But we still don't know how these kind of black holes are formed. So the image I showed you in the previous slide is of a supermassive black hole in our neighboring galaxy. And like I said, there's one in nearly every galaxy. But we still don't know how these black holes were formed. And that's not fun, because all of us love origin stories. Origin stories are important given the amount of movies and things that are out there. Origin stories are important. We really want to know, how did our favorite, superhero or supervillain become the person they are? Like how we really wanted to know, how did Peter Parker become Spider-Man? How did Bruce Wayne become Batman? We really wanted to know, how did Anakin Skywalker become the Darth Vader? And so on. So we love origin stories, and origin stories are important. They help us understand, why did this person become the person they are? And similarly, we need to understand, why is the supermassive black hole, which is such an important entity in our universe, it's there in every single galaxy, and how did it get there, and what is it doing to the galaxy? So it's important to understand how it did get there, and that's what we're trying to find out. So today I'm going to take you through some of our best and maybe not so best theories about how these black holes form, and how we are trying to kind of narrow down this origin story. So just to orient us all a little bit, I'm just going to put a very basic figure. Astronomers, we love figures. They help us make sense of the world. And this is a very simple figure. Just these are the different black hole origin scenarios that I'm going to talk about, arranged according to how likely that it is actually the origin. And on this one, we have how much I want it to be the origin. And as you can see, it's inversely correlated. This is also a metric of how cool it would be if this was the origin. And as you can see, there's always this compromise, which I call the Hubble-Hulk compromise. Again, it's not a real thing, not endorsed, but just goes to say that, sometimes what you really want might not really be the likely scenario. But yeah, we can all go through this journey together. Okay, to start off, we'll start off at the very bottom over here. So as you can see, I really want this to be the origin, but it's definitely not the origin. But this really is how I, came to come about black holes. So it's definitely not from Zorn's head. So any X-Men fans in the house? Okay, so Zorn is a character in X-Men, and that was where I found out about it. So there's all these comics about how, Zorn has a black hole for a head. So they were pretty accurate about the physics. They didn't want it to, open up and they sucked in. But that's definitely not where black holes came from. Black holes are a regular fixture in comics. There's galactus, celestials, and all these evil things which can cause black holes. But that's and I thought, okay, this is why I'm going to study black holes. This is the coolest thing in the world. But it turns out the first thing I realized or found out was that's definitely not the case. Black holes are not from any of these celestial beings or from Zoran's head. So that's definitely ruled out, which is a bummer. You'll have to move on to the next cool thing, which are tiny black holes. So tiny black holes or microscopic black holes are essentially, so we all live in a world where we have 3 dimensions in space. Sorry. Yeah, I can work with it.
Is there another battery?
Yeah, this is what happens when you say but yeah, so little black holes are microscopic black holes. So you have, so the space as we see it have 3 dimensions, and this is how we understand space, and of course we have time. But it's possible that you could have a tiny black hole you could have hidden dimensions beyond your 3 dimensions. And when, the early times of the universe, when space was pretty crazy, let's see if you can go back. Yeah, okay. So early times of the universe, when, everything was so hot and chaotic, it's possible that some of these hidden dimensions could have manifested themselves. So this was something that was theorized and put forward by people like Stephen Hawking. They said, in these small, tiny dimensions, maybe gravity is so strong that you could technically form a tiny black hole. So one way this could have been created was when you could smash particles together and it can get very energetic and you end up with this tiny black hole. So there were theories and mathematical predictions of this, and it got people very worried because when the CERN, the particle collider that came up, I want to say about 2 decades ago, people were very worried and they were like, this is going to cause a black hole to be created here on Earth, and we don't want that. Which is advanced. But yes, so people were very worried that black holes were going to be created. But this is a valid way in which black holes could be formed. But turns out, luckily for us, there have been no black holes that have been formed so far. So people have looked into scenarios, people have still been looking. The LHC has been running for a long, long time now, and we've still not found any evidence of these tiny black holes. So it's possible that they might still be formed in conditions of the early universe. The LHC is still here on Earth. Maybe it's not, doing an extreme job. But even if these conditions were there and tiny black holes were formed, it's very unlikely that they would sustain long enough to become the supermassive black holes that we currently see. So they are going to be very tiny, and theories say that they're going to evaporate really quickly. So it's possible that they could be there, but it's very unlikely that they are the origins of the supermassive black holes that we see. The next one is an extension of these tiny black holes, which are called primordial black holes. So again, very similar to the conditions. Again, I hope this one works, but yes, this is how our universe is supposed to begin, with a Big Bang, and that's when all our galaxies and everything were formed. But the universe in its very origin was very hot and very dense, and definitely a lot more compact. So it was the perfect place to have such immense gravity that you could just form black holes out of the fabric of space itself. And we've tried to look back to these early times, and one way we can do that is because the fact that from the Big Bang, space has expanded, and as space expands, light also expands. So this is light pictured as a wave, and then as space expands, it's also getting stretched out. So it goes to larger and larger wavelengths. So that essentially translates to, again, we'll come back to this picture, but for the purpose of this, very close to the Big Bang, all the light has been stretched out. So as we look back from here, we need to look back in the microwave to see what happened in the early universe. And we've actually done that. We've taken a picture. So this is the universe's baby picture. So this is the remaining or the relic of the Big Bang. So this is the temperature fluctuations that are present when just immediately after the Big Bang. But this is really zoomed in. It was mostly homogeneous. So this is really at very, very small scale levels. And you can see there are these tiny differences between each point. And this is essentially what became the galaxies that we currently see. So there is some precedence that you just needed a tiny bit of this matter in densities to form galaxies. So it's possible that some of these fluctuations might have been so massive that they would have collapsed and formed a black hole at very early stages in the universe. So that is the reasoning behind how primordial black holes are formed. So we have space itself, which kind of collapses into a black hole. So this is a promising theory, definitely can work, but we still have not found any direct evidence of these primordial black holes. People are still looking, so they are still trying to find, but as of right now, we still don't have any evidence or very minimal evidence that primordial black holes were in fact the origin of these supermassive black holes that we see. So it's definitely up there, but pretty low down in the order. Moving on, we come to our top 3 contenders. In number 3, we have runaway collisions. So again, this is collisions between stars in dense clusters. So I think we were having technical difficulties. So unfortunately, it's basically you have stars, so a lot of stars which essentially collide, and when they collide, they're going to be pretty massive, and that can cause a black hole. So this is something that has been seen in the nearby universe. So here you have different star clusters. So this is an X-ray image, so you cannot see the star clusters themselves. So they are shown here when seen in a different kind of light. But you can see these different blobs that they call X-ray sources. And then the authors of this particular study say that these dense nuclear star clusters kind of collided with each other, and then it became so heavy that they just collapsed and formed a black hole. So these dense collisions or collisions between stars in really packed areas can also cause black holes. So that's why it's possible, it's been seen, it's been observed in the nearby universe. We haven't seen a lot of evidence of this in the early universe, but this is still a very promising theory. A lot of simulations are trying to see and understand if conditions in the early universe could form black holes and if they are the origins of the black holes that we see. So this is a promising theory and something people are actively looking at. If we move on to our top 2, we are now here at our first star. So this is something we saw earlier as well. We know pretty well about stellar mass black holes. Again, technical difficulties, but I have a picture. So this is the life cycle of a typical star. This is well studied, well understood. We know the physics, we know the chemistry, but essentially you have a star, so specifically massive stars which go through their life, and eventually at the very end they go supernovae. They eject out a lot of their material, and what leaves behind is a very dense core which collapses and forms black holes. So these are stellar mass black holes that we see all through our universe. So this is well known and well studied. So it's possible that the first black holes were actually formed from the death of the first stars. So this is one of the most promising origin stories, that you just had a star very early in the universe. You should have a star because we see stars all around. There should have been these first stars that were seen, and eventually when they died, they left behind black holes, and these black holes became the supermassive black holes that we see in our present universe. So this is our number 2 for what is a possible origin for these supermassive black holes. We haven't yet seen a lot of evidence for these first stars. We're still looking, which is why it's number 2 on our list and not number 1. And the top contender is something known as direct collapse black holes. So again, anytime you want to form a black hole, you basically need a lot of gas packed into a very small region. So that is what happens. So you have a lot of dense gas in the early parts of the universe, and then they kind of collide, and then because they collide, and then it's very heavy, they need to start collapsing, and when they collapse, it eventually ends up to be a black hole. So you have so much gravity packed into a tiny space, and that is the perfect place to form black holes. So this is direct collapse, so you don't go through stars in this particular process. So this is the astronomy chicken egg problem, which came first, the stars or the black holes. But in this particular case, you just have gas which collapses and directly forms a black hole, which we call direct collapse black hole. So these are our best and worst theories for forming black holes, but why is there an order? How do we know that something is better than the other? Why is this order there? That's because astronomers are trying very hard to uncover this origin story. And two ways in which this can be done. So this is the first one is this is the evolution of time. So this was the Big Bang, now about 14 billion years after the Big Bang. It would have been nice to go all the way back and see how the first black holes were formed, but we cannot do that so well. But here, especially in the early part of the universe, so these are our top two contenders for the black hole origin story, you can see there are some very clear differences at the very beginning. So if black holes were formed in this particular method, so you needed to have very dense gas kind of collapsing, and it is a hard scenario to form. So you don't get a lot of black holes that are formed. So these are little pockets of gas which eventually evolve to become galaxies. You only have some massive ones which collapse and form these black holes, so you don't have a lot of black holes, but the black holes that are formed are pretty massive. When you have stars are more common, it's much more easier to form. They will definitely die and definitely form black holes. So you're going to have a lot more of these smaller black holes present, which eventually evolve. So according to theory of how galaxies evolve, so these small kind of pockets have evolved, and then they merge, and the black holes in them merge, and then these become the galaxies that we see in our nearby universe. But by the time they come to this point, they've essentially lost all traces of their origin. So here there's some very obvious differences, but then by the time we get here to the galaxies, we can easily see we basically don't know how did they get there. But if there were some conditions where some of these initial galaxies did not merge, they did not merge and become these massive galaxies, and then somehow survived unscathed to the local universe, we can study these galaxies and try to find black holes in them and try to understand what their properties are. So if they were relatively unaffected, they did not merge, they just slightly escaped to the local universe, then they should retain the properties that were there in the early universe. So if it was direct collapse, you should find not all of these smaller galaxies have a black hole in them, and the black holes are a little more massive. Whereas if it is this particular method, then all of these small galaxies that we see in the nearby universe, which are very similar to these early galaxies, all of them should have a black hole, and they should be a little less massive. So this is something what I do. This is how I try to figure out the origin story. I look at small galaxies in the nearby universe, and then I try to see if it has an EGN, or see if it has a black hole, and see how massive that black hole is, and how many of these little galaxies actually do have a black hole. Again, as of right now, a lot of our results seem to point that this is the most promising theory. So this is the most promising theories. Not all these small galaxies we're looking at seems to have a black hole, and the black holes in them are a little more massive than what we expect. So it does seem that this is the more promising theory, so which is coming from direct collapse. The other way we can uncover the origin story is by making use of big telescopes. So our most famous one that went up was James Webb. James Webb is an infrared telescope. So again, it helps us look in the earlier time of the universe. Again, if we go back to our standard picture, you have the Big Bang, and as space expands, it expands light as well. So we are essentially, if we look further behind in time, we are essentially looking at infrared wavelengths. So all the light from here is all stretched to infrared by the time they reach us. So to look at them, we need to use the infrared regime of light. And it really is now possible because of this brand new telescope which went just about 4 years ago. So Webb's predecessor, which is Hubble. Hubble is also a wonderful telescope, has done a lot of amazing stuff. But it was a visible telescope, so it only could look in the light we see and a little bit of infrared. But this essentially was Hubble's limit. It couldn't look beyond. But with James Webb, it's really probing these first galaxies. So we really aren't the part where you can see the first stars and the first black holes being formed. We're seeing really, really close to what happened immediately after that. And that's been great. So we have all these different telescopes, and they're looking further and further behind in the universe and earlier times and trying to see how the galaxies were then. And what they found was this? No, kidding, it's not galactus. But what they did find was these little things, and this is exactly what you see. It's a little red dot. But what astronomers think are these little red dots are actually massive black holes that are just being formed, or were just recently formed. So they're very massive. We've tried to measure these little black holes based on different methods, and they're found to be slightly more massive than what we expect. And this is what people think are the signatures of the first massive black holes that are now seen for the very first time. This is nice because we can compare them to different things. So I have another very quick figure. So this is something where you can kind of use to figure out what was the origins of these black holes. So you basically have how many black holes are there at each mass with black hole masses. And then you can make use of simulations to kind of predict what it would be like. So this particular graph is from direct collapse. So direct collapse says you should have this uptick at a certain black hole mass, which is just about 1 million times more massive than our sun. And then if you look at the other theory, it says, the first stars, this is how the distribution should be. So you should have this many black holes as corresponding to each mass. And now we finally have observations from James Webb, and we can put them on these graphs, and this is what it looks like. So there seems to be a trend which kind of agrees with this direct collapse model more. So it seems promising that this could be the origin story we were looking for. Again, it's still very new. We're still finding out more and more, and results are changing every day. It's possible that it might all change, but as of right now, this is what our observations are telling, both from the local universe, using the first method, and by the other method, looking at galaxies very, very far away. So needing to put this all back into perspective, which I guess I need to change this figure because they will not be happy and take my PhD away if I say that I'm on it. So I guess we are all excited about all different kinds of methods of how black holes are formed. And in reality, it is possible that black holes are being formed by all of these methods. But the big question is, what is the dominant method or the most likely method by which black holes are being formed? And really to put this into perspective, we've known about black holes for about a century now. And people have spent all their lives trying to figure out how did they get there, why are they there. But it really is within this past decade or so that we are so close to figuring out what the black hole origin story is. And again, we might be all not wrong, but if I could sit through 7 hours and 1 minute to find out how did Anakin Skywalker become Darth Vader, I think we're all okay waiting a little bit more. But it really is a really good time to be studying black holes and trying to figure out the origin story, because it really does seem that we're finally uncovering this origin story. With that, thank you so much.
Wow, fantastic. So I have the first question. Is the James Webb Space Telescope powerful enough to answer this question?
We think so, yes. I mean, we've been finding all these massive black holes, which really was not possible without James Webb. This was something which is never heard of. I honestly do think James Webb is powerful enough to at least give us some kind of indirect signatures. But we also have other telescopes coming up which can do a better job, in addition to JWST, especially looking at galaxies very close to us. So I think with the combination of all these telescopes, we should be able to get better answers. Great.
So direct collapse looks like the winner.
I hope so.
So how did the universe itself escape the collapse? Because it is so big, Schwarzschild radius has to be large. How did it ever escape to have us here?
So it depends on a number of different things. So the universe itself, so we had the Big Bang, and it kind of, expanded very quickly, very fast. So any of these tiny fluctuations have to be in really small scales. So it's going to be the Schwarzschild radius is not going to be very large. It's still going to be very small. So the universe is at least in theory, it was not in a danger to be to be kind of collapsed. It's just these little pockets which kind of collapse within itself in small regions, and that is how the first black holes form. They're going to be like smaller for sure, and maybe not as tiny, but these are still small regions within the universe's fabric. So yeah, the radius is not large enough for the universe itself to collapse in, and the direct collapse is just it's taking place slightly later. So primordial black holes is what happened like immediately after the Big Bang. The direct collapse is supposed to happen later, so the universe was much more larger, and it really is these pockets where the gas was so dense that it collapsed. So again, the region that we're dealing with is smaller. So thankfully, the universe is not.
I'll provide you a lot more alcohol to get that story right.
Hi. I don't know if this is I don't know if this is a dumb, easy question to answer, if it's a hard question to answer, and I might be too dumb to understand it. But I'm just so confused about what a black hole really is. If it's a star and it has mass, then it ejects a bunch of mass. Somehow it gets stronger and collapses. Like, how does that happen? What actually makes that gravity occur? Like, wouldn't it reach an end? You know, like, if you just kept feeding stuff into it, how does it keep generating power enough to keep growing and never, burn itself out the same way a star did?
Yeah, so there's two different mechanisms. So like to form stars, so a black hole is not necessarily a star. So a star forms under very specific conditions. So it needs to be hot, and then you need to cool it enough so that it actually collapses, and then it has its own way of like generating heat through fusion essentially, which does not happen in a black hole. So in a black hole, it's just at least the direct collapse model, it just collapses with loss of gravity. So when you have so much matter, so you can think of space as a fabric, and then when you put something heavy on a fabric, it kind of curves the space, right? So it's like when you put something so heavy that it just infinitely curves. So that is what we technically think of black holes. So to feed a black hole, you do need to like provide it like things. So there's like all kinds of actions that are happening. So black holes themselves merge, that's how they get bigger. You have gas that kind of falls into the black hole, and that's what kind of powers it. And as gas is falling, it also ejects out a lot of material. So those are different ways in which black holes can grow, essentially, and eventually they reach a point where they don't have enough material. So for example, the black hole in our galaxy does not have enough material, so it's not actively feeding, so it's not actively growing. But it did reach there, the point it is by feeding on gas, by stars that fall into it, by merging with other black holes. So that's how it gets, I guess, bigger in a sense.
So, do black holes die? Or are they forever?
I would say they are forever. Like, it depends on how you define how a black hole dies. But yes, a black hole is just going to, like all these stellar mass black holes, are just hanging out in our Milky Way. So yes, they just continue to be there for a long time.
I guess not so serious of a question, but it's actually more of a question for you. Do you know the tragedy of God is the wise?
Sorry, no.
I was it's a Star Wars joke.
Next question.
It's a nerd thing.
You just mentioned that the black hole at the center of our universe stopped feeding. Our galaxy, why did it stop feeding?
Yeah, that's a great question. So it depends on how much gas it is available in the surrounding next to it. So this, again, an active black hole is actively feeding on gas that's surrounding it, and eventually either all the gas falls in or all the gas is expelled out. So there isn't just enough material close enough to the black hole to actually fall into the black hole to kind of feed it. So it eventually runs out of fuel, and that's when it kind of becomes inactive. It just ran out of material in our particular.
I'm an scientific dum-dum, and I'm scared the Hadron Collider is going to create a black hole that grows bigger and bigger and sucks the Earth into it. What do you say to people like me?
I would tell you to not be worried because that's definitely not going to happen. And that is what a lot of people have actually gone through the physics behind it and to check first of all if that could happen, what would happen. But all the results currently point that even first of all there's been no black hole that's formed. They've been smashing particles for years now, and that has happened. And even if a black hole is to be formed by a collision in that way, it's going to be so small that it's going to instantly evaporate. It's never going to get big enough to swallow anything. So you don't have to be worried about that. So don't lose any sleep.
You mentioned that one of the suspected ways that they form could be two clouds of dense gas that meet. Does it matter what gas, what makes it dense? And second question is, you also mentioned that we've known about black holes for 100 years. Is that when they've been confirmed or how long they've been suspected?
Yeah, great question. So the first one, yes, there's a very specific condition for this gas to be, because otherwise, there's still gas in the universe currently, and we should be forming black holes even right now, but that doesn't really happen that frequently. So it really is very unique conditions in the early universe. So the gas has to be very pristine. It should not have a lot of metals. So metals for astronomers, anything other than hydrogen and helium. So these metals are really very good at cooling. So the more metals you have, you're just going to cool. So it's never going to be hot and dense enough to directly collapse. That's when it's more likely that it's going to form stars instead. So that's why. So there's very specific condition. You need to have very hot, very dense gas that's mostly just made of hydrogen and helium, and that is what essentially collapses to form the first black hole. So that's why we're not forming them right now. So now the universe has evolved so much that we have plenty of metals. It's very metal rich, and that's just going to cool down all the gas instantaneously. So you're never going to get hot enough to for gas to collapse and form a black hole currently. So those are the conditions for the gas per se. And then, sorry, I forgot your second question.
We've known about the black hole.
Yes, yeah. So yes, we've known about black holes. So actually, black holes as a theory was actually around for about 2 centuries. But the whole point, yes, black hole as a theory. So this was when people started finding out, when stars died. So they found all these what should happen, when people started thinking about Einstein came about with gravity, and he redefined gravity as this curvature in space-time. So people started thinking about what if something is so massive that it just infinitely curves space-time. So it's been around 100 years as a theoretical concept. It's been indirectly proved for about 70 years. So we've had indirect evidence of black holes, but we've never seen a black hole itself. It really is. So the image that I showed you was in 2019. So it really is, I want to say 6 years that we know. We've taken an image, so we know for sure that there is a black hole. And they gave the Nobel Prize in 2019 because Nobel Prize, they want proof. So it really is. So even though we've known about black holes for a long time, it really is just over 6 years we've actually taken photographs, and we know for sure that we're not making this up. So.
Okay, last question comes from Twitch. Are the observations from LIGO important to our understanding of black hole evolution?
Yes, absolutely. LIGO is great. LIGO is actually one of the, first. So yes, LIGO essentially detects black hole mergers, and then it kind of gives you. It's a good way to measure the mass of the black hole, which is important for us. And that's how. So LIGO was one of the first. It gave us the first measurements of an intermediate mass black hole. So these are black holes which could come from the first stars. So that was essentially very exciting because they were we've never had this confirmation. So yes, LIGO and its predecessor or its successor, LISA, which is going to be up in space, is going to give us a lot of information. So LIGO can only do so much from Earth. It's kind of limited, so it's not giving us, it's not telling us how many of these, small black holes are there currently. But yes, all these gravitational wave observatories is very important for measuring the mass of the black holes, especially in our nearby universe. So if we look at the other method, where we look at nearby galaxies to kind of measure the black holes to kind of pinpoint the origins, LISA and LIGO is going to be very useful for that.
And for the audience, LIGO stands for?
laser interferometer gravitational wave observatory. So, yeah.
And with that, I think we are done. Thank you.